Welcome to The Explainer. We're going to be diving into some fascinating new math today to try and answer a question that, well, it affects pretty much all of us.
All right, so let's just jump right in. I mean, it's a huge paradox, isn't it? We are more connected than ever before in human history. We've got all this information, all these ways to talk to each other. And yet, it feels like we're just getting more and more polarized, splitting off into our own little camps. So what is going on here? So for a long time, the science of networks, the traditional models, they really had a tough time explaining this. The math just wasn't matching up with reality. And that's because the early models were based on this very simple, kind of intuitive idea that, well, it turned out to be totally wrong. See, the old math predicted that if we all just talked to each other more, our opinions would kind of blend together, right? Like mixing paint. We'd all average out and eventually reach a consensus. But just look around. Reality is the complete opposite. It seems like the more connected we are, the more polarized we get.
So, this major failure of the old models forced researchers to go back to the drawing board, and they came up with a new idea, a whole new framework. The problem wasn't just what we believe. It was that the models were missing this incredibly important, very human piece of the puzzle, the difference between our inner thoughts and how we actually talk about them out loud.
And to model all this nuance, mathematicians pulled a tool from a really advanced field called algebraic topology. Don't worry about the name, but the tool is called a discourse sheaf. And its entire job is to make this crucial distinction between our private beliefs and our public words. So a discourse sheaf, think of it as a special kind of map for conversations. It creates a mathematical separation between two things. First, your private opinion space. That's what you really truly think inside. And second, the public discourse space. That's the actual words you use in a specific situation. It's the simple idea that the way you talk to your boss is probably different from how you talk to your best friend, even if you're talking about the same thing. This math actually accounts for that.
Okay, so how does this thing actually work? How do you build a model with it? Well, it all breaks down into three key building blocks. First up, you've got your private opinion space. This is basically you. It's your internal world, your complex belief system, what you actually feel about things. The fancy math term for this is the vertex star. Next, there's the discourse space. This is the conversation itself. It's the specific topic on the table between two people. It could be something simple like, where should we get lunch? Or something heavy like politics. In the model, this is called the edge stock.
And this is where it gets really interesting. The third piece is called the restriction map. This is the translator. It's the mathematical rule that takes your super complex private opinions and maps them onto the simpler, specific conversation you're having. This is the magic step. It's how the model captures you choosing your words or changing your tone. Maybe you exaggerate a bit or, tell a little white lie to keep the peace.
So when you put all three of these pieces together, the model shows us something fascinating and maybe a little bit uncomfortable about how we all get along. It reveals how we can create social harmony, how we can all agree, without anyone ever actually changing their mind.
Okay, so let's picture the initial state. High discord. You've got two people, and their private beliefs are totally different. When they first start talking, they're being honest and clash. Their opinions don't line up. You can feel that social friction, right? Then the model runs a simulation. And here's the key, their deep down opinions don't change, not one bit. But they both sense that friction, that disagreement, and to make things smoother, they start adjusting how they talk. They start tweaking that restriction map. They literally learn to express themselves differently to minimize the conflict. And what happens? The system settles into what the math calls a harmonic state. It's stable. On the surface, it looks like everyone agrees. But dig a little deeper and you see that their private beliefs are exactly the same as they were at the start. One of them, or maybe both, has just learned to lie is a strong way to put it, but they've learned to adjust their words to create the appearance of agreement. Okay, that's a huge insight, right? But it opens up an even bigger can of worms. What if the problem isn't just that we're being strategic with our words? What if the very tools we use to communicate, our language, our data, are themselves limited? What if they're not perfect? Let's chase that idea, because it leads to a whole other breakthrough.
So there's a second, totally different mathematical approach that looks at this whole problem from another angle, precision. It borrows ideas from number theory to measure disagreement at different scales, almost like zooming in and out or changing the resolution on a photo. Think about it like this. In a perfect, ideal world, information would be perfectly smooth, continuous. But that's not the real world. In reality, all of our data, our measurements, even our words, have a limited precision. They're quantized. They come in chunks. It's like the difference between a high-def photo and a blurry, pixelated one. Some inconsistencies, some disagreements, you can only even see them when you zoom way, way in.
So to navigate this kind of pixelated world of information, mathematicians came up with this really clever tool. It's called an arithmetic barcode. And you can think of it like a scanner that goes over a whole network and finds the unique signature of every single inconsistency, no matter how big or how tiny. This is just a brilliant way to visualize it. Every single bar in this barcode points to a specific disagreement in the network. But here's the cool part. The length of the bar tells you how much you need to zoom in to even notice that disagreement. A really long bar? That's a huge fundamental conflict. It's so big you can see it even when everything is blurry and low res. But a tiny little short bar, that's a super subtle inconsistency, a little bit of friction you would only ever spot if you were looking at everything with a microscope with super high precision. And look, this isn't just some clever trick for analyzing Twitter arguments. This is a whole new language for looking at any complex system where information is flowing around. It doesn't matter if it's a social network, a digital one, or even a physical one. Like the researchers themselves say, this completely flips the script. All those little inconsistencies, the things we used to dismiss as just noise in the data or a measurement error, well, now we understand that's not noise at all. That is the signal. That torsion, that little bit of disagreement, that's actually the most important information you've got. And the real-world applications for this are huge. Think about a network of sensors. A tiny little disagreement in the data that only shows up at high precision could be the clue that one sensor is broken. Or in financial markets, a subtle inconsistency between different data feeds could be the very first warning sign of a crash. You could even use it to help a team of robots coordinate better, helping them reach an agreement even when they can only send each other simple pixelated messages. It's like we've invented a whole new kind of ruler for measuring the invisible friction inside complex systems. Which brings us to a final, pretty mind-bending thought. If our disagreements aren't just about what we believe, and they're not even just about how we strategically talk about what we believe, what if they're also shaped by the very precision, the very resolution of our language and our data? It makes you wonder, right? How many of our deepest conflicts are actually real, and how many are just illusions, just ghosts in the machine created by the blurry tools we're using to look at the world?